So we're going to start this video from a small correction in my previous video, and for that I'm just going to erase this input power thing because that value is kind of wrong. I'll tell you why. Okay, till here whatever we did on our last video is correct, but in this case for 5-volt input whatever I did was there is a little correction on that. All right, so let's move to that thing. All right, so what I did, P in is equal to P out plus P loss, but for P loss I'm just going to change the color. Okay, so P loss will be V in minus, sorry, P loss will be P in minus P out, right? That will be the loss. Then what is P in? P in is V in into I in minus P out will be V out into I out, correct? We know I out. In case of LDO, there is one thing, because this is a passive component circuit, so whatever the input current will be, it will be equal to the output current. Okay, it will be independent of voltage input and voltage output. So that means in this case what will happen, it will be V in minus V out. Okay, if you want you can simulate that on TINA tool. On that there are a couple of LDO given by default by TI. LDO libraries are there, so you can just simulate that or pick one LDO from example, and you can see this is something I got to know today. I was thinking it as a IC or something like that, which has like complex circuit, and on that it works like transformer, like power output is equal to power input, but there will be some efficiency thing. Okay, but I'll tell you what is efficiency mean for LDO. So here this will multiply by I out. All right, what is our V in? V in is 5 volt, V out is 3.3 volt, and I is we have calculated 0.164. all right, I'm just going to zoom out a bit. Okay, I hope you got my point, right? All right, now we'll do this calculation. Open calculator, and this will be 5 minus 3.3 multiplied by 0.164. This will be the power loss. All right, so power loss will be 0.27 watt, right? This is P loss. Okay, now for calculating, so here we don't need to calculate what is the amount of current which is flowing from here, but I wanted to tell you this thing, right? This is what I kind of forgot to tell you on last video, right? So this is how you calculate the power loss for LDOs. Okay, let's move to our tutorial of power distribution network analysis for this complete power budget. Now before going further, I just wanted to remind you about giveaway that is going on our YouTube channel. So you don't need to do anything else, just fill the form given on first comment and you should be a subscriber to get free access of Altium PCB Udemy course. That's it. Okay, let's move to our Altium Designer project, and this is our board file. Before starting the power distribution network analysis, there should be one thing, there shouldn't any DRC error on board file. So you have to run DRC check and resolve all the warnings and errors. Okay, only then you can able to run power distribution analyzer. So here I wanted to add one more point. before going for power distribution network analysis, I would suggest note down all the nets. So for example, to simulate this particular connection between VCC and ground, you have to note down this particular net, because that node or that ground, we know it's ground net, right? If you'll hover cursor here, you can see it's ground net name. But with this one, we don't know what is the name of this net. So you have to just hover cursor, and it is net ds1_a. Okay. Similarly, note down for whatever the network, for whatever the circuit you wanted to analyze PDN, you have to note down the net name, because we're going to include all these net name. I'll show you how. So I've already noted down all the nets here. Now we'll go to our project file or board file, tool, PDN Analyzer, and this window will pop up. Here qualifiers, as I told you on my previous videos, qualifiers are all the net names, different type of notations people use. Some people use positive 5 volt, some people use 5 volt, some use 1.8, some use 1V8, right? So these are all kind of notations for power ports are here. And if we check all these check boxes, Altium will automatically pick all these nets from your schematic, right? Now here, as you can see, all these nets or net names are picked by Altium designer using these qualifiers. All right, and now we'll just select all of these first, okay, and we'll fill the correct voltages here, because for NRST and VCC, Altium basically it don't know like what is the voltage for VCC, right? But it knows it is a power net. So in our case it is 3.3. Similarly for NRST it is 3.3. Ground will be 0. Now we'll do add selected. So it will just transfer from this to this, right? So that means we're going to use these nets for PDN analysis. Now there are few more nets we need to include, but Altium can't able to identify those as a power net. So what we'll do, we'll just enable all nets for filtering, and as I told you, I have already noted down. So one is D plus, there is a pull up on this one. As you remember, it is 3.3. We'll select, add selected. Now you can do one by one, or you can do all together as well. I prefer one by one, because it's a kind of finish all the task, or there's like less possibility of any kind of error there. Anyways, for LED, it is again 3v3, right? 3v3, add selected. Apart from that, NRST is already there. So yeah, these are all the nets that I wanted to include. 5, 3v3, ground. Make sure you are including ground in case you are using some isolated grounds in your different kind of circuit, right? So don't miss any power net, otherwise you'll get kind of partial results in PDN analysis. So these are all the nets selected. Now I'll just disable this thing, and I'll make sure there are no unselected nets. Okay, so in case there are something, we can just select and reject those. All right, so let's press OK. So here I'm just going to hide this bottom message thing. So we can just, there's an option in this PDN Analyzer. You can make it compact. Left click on File and left click on Compact Layout. So what will happen? It will just hide it and make it like more compact. Now I'll just make it a bit bigger, so it will be like full network is clearly visible. And here we have different tabs. So instead of like watching everything parallelly, we'll just switch between the tabs to see all the results and everything. All right, so this is your default thing. You have to enter or create the power flow it's very similar to our power budget, so that's why I used to create power budget before going for any analysis of power distribution network. Now here, if you left click here, you can get this option edit net, and from here we can able to select what will be the net here. So we know our input is 5 volt. Okay, so we have selected 5 volt. Similarly, we'll select ground. Okay, this is something like very basic network that we have created. Now next step is we have to define from where this 5 volt is coming, right, or the source. So for that we'll just left click here and we'll get this option add source. We'll just select it. Now if you'll go back to your schematic, okay, hold on, let's close this one, go back to schematic. Here you can see the power is coming from this J1 connector. Okay, so we'll just again click here, add source. Now what is we are adding? We are adding a voltage source, right, which is our J1 connector, right? So you can verify these are all the ground pin on J1 connector and power pin is first pin, right? This is our source. Now what is the maximum current a source can provide? So generally we're going to connect ST-Link with our laptop or PC, and for USB 2.0 maximum current out from a PC can be 500 milliamps, right? This is very general, so I'm just going to put 0.5 here. All right, and V out will be 5 volt. I'm not going to consider any series resistance there. So this is another thing is maximum power pins current. Okay, this is again, so it is asking for whatever the pins we are using in connector, is there any limit on current, limit current there as well. So generally it happens for high current. For example, you are using a JST connector for 5 amps of power source. So I guess it can't able to handle that amount of current, a DC current, right? So these are all the information you can enter here, but in our case it is fine. Okay, so here our source is added. Now where this 5 volt is going, it is directly connected to a regulator. Okay, now how to add regulator? So here we'll just right click and here we'll add load. Okay, now our load is a linear regulator, so we'll just select this. All right, what is the designator of linear regulator? It is U1. And what is output? It is VCC. Okay, U1. Pin number 5 is output. You can verify. 1 and 3 is input. 1 and 3 is connected to enable. You can also edit that if you want to remove the enable thing, right? Because in our case it is just first pin, right? Okay, so these are enough information. Now here we have to enter what is bias current, that is fine. Limits is very important. So what is the I out from this regulator? Okay, you can see this is output, this is input, right? And this is a basic circuit of a regulator. So what is the I out of this regulator? We have already discussed, it is 0.164, right? Power dissipation and maximum power pins current. This is again the same thing. Power dissipation we have calculated, right? So what is the amount of power will dissipate? It is 0.27 watt, right? So we'll just enter 0.27 watt. And that's it. Okay, this is connected. Now this particular network is further powering up other things, right? So what are those? So to do that, we have to just right click here again and click over new network. Okay, so here new network is again created. Okay, one mistake, so I'll just delete this. What you have to do, you don't need to click over new network, you have to click over add VRM to new network. Okay, now this is fine. So now this regulator will act like a source, and there will be further loads like LEDs or some USB pull up, right, or NRST pull up, like that. Okay, now here we have to enter, these are all act like a load. There's nothing like a series thing on those, right? So there will be multiple loads on this VCC or 3.3 volt. I hope you're getting my point, right? That's why we have created, I'll show you here. So these are all the loads on this one, right? Nothing like in series or some series component are there, right? These are all act like a load. Okay, let's do that. So there is one load which is this chip itself, which is U2. Okay, so I'll just click here, add load. Load is IC and it is U2, right? So it will consider all the VCC pins and all the ground pin, right? This is how current will flow. Now what is the load current? So from our block diagram, for this load current is 150 milliamps. Okay, so it will be 0.15 amp. For voltage tolerance, I'm just going for plus minus 5%. Okay, it can vary like that, and press OK. One load is added. Let's add another load, and this time we'll go for 10K pull up on RST. Okay, so what is the designator there? And that designator will be our register. Okay, so hold on, I have to close it because I can't able to see that designator. Okay, now I can see. Add load, it will be register. Okay, and R8, it's selected. Ground will connect through SW1. Okay, so this is the complete circuit. When switch will close, it will act like a load. Set parameter, you can add 10K. It is in ohm, so you have to enter 10,000. Voltage, I'll go for don't care for this one because it will not vary, and press OK. Okay, so it will automatically calculate the value here. Okay, there's one load here. Now we have to add another load, and this time we'll consider two LEDs. Okay, so we can't multiply them, so that means we have to add LEDs individually. All right, again we have to see the designator of LEDs, so let's zoom in there. It is DS1 and DS2. Let's add those. LED will act, so there is series register on LED as well, right? So I'll just put a register there, and because that is the where that is a kind of load for the load which will define the current for LED, right? So that will be R6, and ground will be through DS1. And what will be the resistance? Resistance will be 510. This will don't care. Press OK. Now we'll add another load. that will be for this LED 2 or DS2. It will again a register. VCC will be connected to R7 and ground will be through this D2, okay, DS2. So you'll not find DS2 here because this this is connected to PC13. Okay, net name is PC13, and we are considering it will be internally pulled down. Okay, so what internally pulled down means the current will flow through the grounds of our controller, right? Let me know if I'm doing anything wrong, or in case of any doubt, just put your comment, I'll reply there. So our chip is U1, it's U2, sorry. Okay, so through these grounds it will be here. What is the resistance? It is again 510 ohm. This will don't care. And okay, all right. After LED, we'll add pull up of USB. All right, so its ground will be this connector's ground. So add another load. This is again a resistive load. So this is a kind of very simple circuit. Later we'll do like really complex ones. So this one will be R3 and ground will be J1. Okay, all right. What is the resistance? It is 4700. Voltage we don't care. All right, so these are all the loads which is connected. Now we'll go and save this file. We'll save it as a PDN network. All right, so these are two networks that we have discussed from block diagram to our declaration on PDN Analyzer tool. Now here you'll see these check marks. That means all these things are ready to simulate. We have entered all the information here. Okay, now for simulating this, we have to just left click over analyze. So this analysis basically generate ODB++ file, and it take information from your stack up and do all the analysis. All right, so here we got one error. We'll see what is that error. To see where is this error, what we have to do, we have to just hover our cursor here, and it is something related to power dissipation. Okay, so okay, so if you remember, we have defined the power dissipation here, and as expected our power dissipation is slightly higher than the actual power dissipation. Okay, so let's double click on this one, and here we have declared 270 milliwatt is maximum power dissipation that we can handle, right? And actual power dissipation is 279 milliwatt, right? So it is under the limit, right? If there is a 9 milliwatt extra dissipation, it will not cause that amount of heat up through voltage regulator, right? So we're just going to consider it 280. All right, and then click OK, and again it is resolved, right? So again, this is a kind of, now we'll know what is the power, what is the amount of power that going to dissipate through this 3.3 volt LDO. Right now we are not getting any error, but on later levels I have basically created few type of error which you will going to see in your projects when you will go for power distribution network analysis. And yeah, I just wanted to cover all type of errors, so it won't be kind of unknown when you'll try this for your design. Now let's check other tabs. So on message, yeah, these are all the violations. These are basically all the logs, whatever we did. This tab is kind of very important if you want to customize the report. what are these tabs? So we'll go through with them one by one. First is voltage and current density. So here you can see this particular you can say scale is for voltage right now. You can denote it as a rail, or you can just display the voltage. So this is the voltage variation throughout these tracks. Okay, so what is the meaning of this? Like, it is varying from 3.3 to 3.29, which is very low in this design. But if you are using really thin tracks, or if you are using some switching supply, it can be really bad. So this is what PDN will be very helpful. But in this case, it is kind of DC, and it is varying 0.01 volt, which is tolerable. All right. Similarly, you can check current density. So current density is a scale from 0 to 20 amp per mm square. It's a huge amount of current which is flowing here. So these are all the things we can collect and put those in our report, and like during review meetings or whatever, like how you want to handle that report, we'll basically discuss this amount of current density or voltage drop is okay for this particular net or not. Okay, show arrows is nothing, just it will show the current flow, right? So from where current is generating, okay, so it is going to this one, it is generating from here. You can see these arrows. Okay, not generating from here. Okay, this is the source, it is generating from here because this connector is here, USB, and from here it is flowing to this one. All right, similarly here you can switch between the ground. You want to see ground, you want to just uncheck VCC, you want to switch between layers, you can do that. Similarly, another is peak value. You can highlight where is the peak current. So in this section it is peak current, as you can see from a scale, as it's like more red here. Okay, you can highlight that what is the value here. And similarly you can go for minimum. Minimum is on bottom layer, this blue part you can see. And yeah, it can locate that. If you wanna check second maxima, you can see second maxima is somewhere here. So that's really important. So what I basically do, for example, I found this first maxima. Okay, this is something which is kind of critical, can be a critical part. So what I'll do, I'll just image capture. Okay, and this will be this is on network VCC, and this is screenshot 001. Done. So it will be included on report when we'll generate that HTML file. All right, similarly you can get slider. So here you can put a percentage value. So this is 0 to 20, as I tell you, this is 100%. Okay, so 50% will be around this 9.5 or slightly less than that. So it will kind of mark that particular location where it is 9.05 for 50%, right? So it's kind of things you wanted to probe, you can do that. Another thing is this side. So same thing you can view on 3D and put overlay. So this will kind of give you rough idea. So what are the components which are participating in particular net, right? And yeah, this is what you can do that. Okay, so I personally prefer 3D with overlay. So it just when you capture the screenshot, it just give a rough idea how that track is going from different components, right? That is one thing. Another is pin wise. So these are all the components, their pins and their voltage, and whatever the voltage is there. So you can short those, what is the minimum voltage. So on U1 ground there is some microvolt, okay, with some amount of current. It shouldn't be there on ground pin, so you have to see why it is there and what are the cause of these, right? But it is microamps, so you can ignore it, but again it depends on your design how critical it is. Similarly, you can short it with current. So this is the max amount of current which is flowing, this is the minimum amount of current. As I told you, we can able to see what is the voltage across via. So this is starting layer, this is ending layer, this is our first via, this is the location of via. These are the voltages, which is quite similar. What is the amount of current which is flowing through via, right? So these are all the things that you can consider as well. Similarly, in this table we have all the test cases, what are pass, what are fail test cases, what are the load pin. It's the same thing from this thing. We'll see. Okay, this is the information about source, right? So it's quite easy to understand these things. Now here I've done these things default, right? In next level, I'm just going to tell you how to change the PCB property and how this thing impact on the conductivity and the resistivity of the material that we are using. All right. So again, that is for next level, and it is again very important part if you are using different types of materials. One more thing I wanted to tell you, this last thing, which is report. So if you just left click over this one, and it will generate all the report. So we have captured only one image. You can capture a couple of images like maxima, minima, where is the maximum voltage, where is minimum voltage, where is maximum current density, minimum current density, like that. And then left click over generate report. Report is generated. Double click on this one. I'm just going to open it on Chrome. All right. So here you can see this is stack up information. This is our artwork of top and bottom layer. This is the setting that I'm going to tell you on next level, and this is our pass. Both of the network are pass here overall. The total power consumption, right? So I would suggest go through with this report. Project is already attached in this tutorial, and try to do it by your own. And yeah, in next video we'll just go in very depth about this particular tool, and their power budget will be a little bit complex. So yeah, this is what I wanted to tell you in level 1, and let me know in case of any doubt in comment section. Thank you.